I'll start with my presentation about solar system small bodies. So it's the second part of the lecture on small bodies in our solar system. The first part was giving the laboratory perspective of studying rocks, so meteorites found on the surface of the Earth. And here I'll give you the astrophysical perspective. So it's more related to what I do here at ISO. In case you missed the first lecture, I'll give a brief summary of why we care so much about meteorites and small bodies in our solar system. But the recording is available on the web page of the lecture series, and it's also on my YouTube channel. Don't forget to subscribe. So we care about meteorites because they are our primary source of information about our protoplanetary disk. At least some meteorites, actually the majority of them, they have preserved information in their composition about the early solar system, about the thermal and chemical condition that prevailed in the protoplanetary disk. And I also talked.
I don't think you're sharing your screen.
Oh, sorry for that. Let's see. Share meeting. Is it working now? Is it working? Yeah. And so I talked a little bit about. I don't know if I can hide this.
And minimize it also.
Okay. And I talked a little bit about paleomagnetism, which is the study of ancient magnetic field, which is recorded in ferromagnetic minerals inside rocks. In that case, meteorites, and that remaining magnetic field can inform us about how the early solar system evolved and how the protosolar nebula dissipated over time, right? So meteorites are a primary source of information about our protoplanetary disk. They're also primary source of information about planetesimal and planet formation. So we have differentiated meteorites that come from the interior of differentiated planetesimals, sampling the different compositional layers from the core to the mantle to the crust. And from the isotopic study of these objects, we can get the precise timing of planetary growth from micrometer dust to microscopic aggregate to pebbles and multi-kilometer size objects. So that's all in the first lecture. So you can have a look at this if you're interested. So now I'll give you the astronomical perspective about studying small bodies. So I'll start with where meteorites come from in our solar system. And as you probably know, they mainly come from small bodies, asteroids, and comets. We have a very tiny fraction of meteorites coming from the moons and Mars, but most of them, 99.9%, come from small bodies. And we have different reservoirs of small bodies in our solar system. We have the main belt, which is located between the orbit of Mars and Jupiter. Sometimes main belt asteroids, they get a little bit too excited by Jupiter, and they end up on the Earth-crossing orbits. So those are called the nearest objects. So nearest objects are asteroids or comets with non-zero impact probability with terrestrial planets. Then a little bit further away on the orbit of Jupiter, we have these two swarms of objects which are dynamically stable on the L4 and the L5 Lagrange point of Jupiter, so 60 degrees before or after Jupiter. Those are called the Trojans. Actually, other giant planets have Trojans like Neptune. And if we zoom out in the outer solar system, so beyond Neptune, we have the Kuiper belt beyond the 30 astronomical unit. The Kuiper belt is a very interesting region if you're interested in deciphering planetary migration during the first million years of solar system evolution. And so the Kuiper belt is composed of two main dynamical population of objects. You have the dynamically cold population, which is a remnant of the early disk in our solar system. So those are called the cold classical objects. And one beautiful example is Arakoth, which was visited by the New Horizons. Which strongly interact with Neptune, and one of them is Pluto. So Pluto is in a 3-2 mid-motion resonance with Neptune. So each time Neptune goes 3 times around the Sun, Pluto goes twice, and Pluto even crosses the orbit of Neptune. But because they are in these synchronous orbits, it's never scattered by the planet. And there's a lot of TNOs like Pluto in these mid-motion resonances. So just like nearest objects are fed from the main belt, we have a population of objects with lower perihelion than capable objects, which are called the centaurs, and they are a transitioning population of objects between the Kuiper belt and the short period comets. So short period comets are comets with orbital period of less than 200 years. And they are mainly they come from the Kuiper belt. And then if you zoom out even more, there's this hypothetical population of icy bodies from a few thousand million to 100,000 astronomical unit, which is called the Oort cloud. And it was never directly detected, but its existence was inferred from the detection of because we have long period comets with on high orbital inclination orbit in our solar system. All right, so that's for the different population. So what do they look like in real life? Because we have this very biased view from science fiction movies. So here is an image of the Focomillennium. That's how you call it in English. Yeah. Sorry? Millennium Falcon navigating through an asteroid field, and it's pretty dense, as you can see. So that's a nice assignment that I like to give to undergraduate students. It's kind of fun knowing the radial extent of the asteroid belt and its orbital inclination, which is about 10 degrees if you have objects on the higher inclination orbits. But you can compute the volume of the torus center around the Sun, and knowing that you have about 1 million asteroids larger than 1 kilometer, you can compute the average distance between objects in the main belt. And if you do that, the average distance between kilometer-sized asteroid is about 4 or 5 million kilometers. So this is not very accurate. And yeah, of course, these objects are smaller, but if you use meter-sized objects, there's still a lot of empty space in the asteroid belt. So this is wrong, but George Lucas at least got one thing correct, which is that the asteroid belt is a very dynamically active place still today. You just have to look at the sky parallel and you see all these shooting stars. Obviously, they're coming from somewhere. So the solar system is very active, and the Kuiper belt is the asteroid belt is evolving today through different physical mechanisms. The first one are stochastic collisions between small asteroids. Then we have thermal forces from the Sun that plays an important role. So if the projector is the Sun and I'm an asteroid, and so I receive photons, I reflect part of the photons, and I also absorb some photons and I thermalize them. And by the time I remit them as thermal radiation, I'm rotating. So if I'm a prograde rotator, I will the exchange in angular momentum in a given direction will make me drift towards or away from the Sun. So if I'm a prograde rotator, I'm going towards the Sun, and if I'm retrograde, I'm going in the other direction. Okay, so that's what we call the Yarkovsky effect, after the person who discovered that effect. Then we have dynamical pushes during close encounters between small bodies in the asteroid belt or with planets, with Mars, and especially Jupiter and Saturn. And then we have space weathering. So space weathering is a very general term to that groups a range of physical mechanisms that alter the surface composition of small bodies. So that can be irradiation, bombardment by solar wind, micrometeorite bombardment, and in many different ways it can alter the surface of asteroids, and that sometimes makes it complicated to understand what their composition is, because we don't know what's the actual composition and what was altered by space weathering. So if we combine these different mechanisms, we can explain why we get meteorites on Earth, why we get collisions with asteroids, why we got extinction events in the past. So here is an orbital plot of the asteroid belt in orbital inclination as a function of distance from the sun, semi-major axis. And you can see that the objects, they are not randomly distributed. There's quite some structure in there, right? And you have these vertical empty zone and lots of clusters. And these clusters, they actually originate from collisions. So they come from the disruption or a cratering event on an asteroid. And the cluster is originally very localized in semi-major axis. But here you see this very long horizontal filament. And of course, the initial velocity distribution of fragments plays a role, but what really makes this long horizontal filament extend in semi-major axis is the Yarkovsky drift. So in the families, you have small fragments, and they are very sensitive to this force. So the large asteroids, they stay where they are, and you have the Yarkovsky drift is optimal for meter size or objects of a few tens of meters. And if the objects are too small, well, the heat wave propagates throughout the whole body, and they emit radiation isotropically. So that doesn't affect their orbit.
Can I ask a question?
Sure. Yeah.
Is the sensitivity complete the map, or are there places where you cannot detect?
Sorry, I didn't get that.
The sensitivity of this map, is it complete?
Oh yeah. Well, to a certain size, yeah.
Okay, but in base and inclination, it's
Yeah, except maybe for, okay, we don't go up to the Jupiter Trojans, but for those will be the Hildas, I guess. Yeah, I would say, I think the completion limit for the inner belt is around 1 kilometer, and for the this part of the belt would be around 3 or 5 kilometers. So back to these clusters, so we call them collisional families because all these asteroids, they belong to the same family. They all have a common origin. And as I say, smaller fragments are more sensitive to thermal forces. So if you actually plot the invert size of the family members as a function of distance from the sun, semi-major axis, you find this very characteristic V-shaped diagram. And that's again because big fragments, they stay where they are, and smaller fragments, they are sensitive to this radial drift. And it's pretty neat because if you have a very young family, so this V is really narrow, and over time it will extend. And so if you have an accurate dynamical model, you can actually derive the age of the family by fitting the envelope of this V-shaped diagram. Okay. So this family fragment, they extend, but at some point this has to stop, and this stops when they actually reach this regions where you don't see any object, these vertical regions, which are actually mean motion resonances with Jupiter. So for instance, this one at 2.5 astronomical unit is the 3-to-1 mean motion with Jupiter. When an object enters this resonance, you will get these periodic dynamical pushes by the planet. And so it will evolve from a rather circular orbit to something very, very eccentric. And eventually it will cross the terrestrial planet orbits. And that's how you get meteorites and impacts and all of that. All right. So we care a lot about small bodies in our solar system because they are very excellent tracers of planetary migration. So let's say for a very long time, the dominant view of planetary formation was that planets are found today where they were formed. Of course, this changed with studies of exoplanets and the Kepler telescope, who found all these giant Jupiter close to the stars, and obviously they couldn't form there, so they had to form far away from the star, and they migrated inward. But even before that, they were a very strong indication for planetary migration in our own solar system. So here is an old plot from the 80s showing the distribution of asteroid types as a function of distance from the sun. So each letter corresponds to a specific type. I'll tell you more about compositional types later on. But from this plot, you can see that there's some compositional stratification in the inner solar system. So each type is dominant at a given in numbers and also mass at a given distance from the sun. But you can also see this overlap. So this compositional gradient was inherited from the protoplanetary disk, but then you see this overlap of compositional types, and this is because of Jupiter migrating and scattering objects around. Okay, and if we go to the outer solar system, to the Kuiper belt, there's also very strong indication for Neptune migrating outward. So as I told you, the Kuiper belt is made of two main populations: the cold disk, which is a relic of the early protoplanetary disk, and those are these red objects which are found. So this plot shows orbital eccentricity as a function of semi-major axis. So you have this cold population that is weakly interacting or not interacting with Neptune, and then you have the object that strongly interact with Neptune. So you have the scatter disk. So these lines show perihelion distance, so closest distance to the sun at 30 AU. So Neptune will be here, and this is 40 AU. So you have this scatter disk or scattering disk, because these objects are strongly interacting with Neptune, and sometimes they get scattered inward and they become centaurs. So this transitioning population between Kuiper belt objects and short period comets. Centaurs are in orange here. And then you see this fingers, this population, which are resonant population. So this one, the most populated one, are the Plutinos, and they were named after Pluto because Pluto belonged to this population and was the first object to be discovered. But all this population is going twice around the sun each time. Neptune go 3 times, and as you can see, they reach this perihelion distance of 30 AU, so they are sometimes closer to the sun than Neptune. And this resonant population, they are overpopulated. They could not have formed in situ, so you actually have Neptune migrating outward and pushing objects into these resonances. So that's another indication of planetary migration. And to show you how that happens, here is a very nice simulation by Shen Raymond, showing a giant planet migrating into a disk of small objects, and you see the formation of these resonant populations. object being scattered and ending in a scattering disk. And in this simulation, you're left with a small belt of cold objects, dynamically cold objects. It's pretty cool.
So basically, this simulation shows that you never have any cold disk again after the planet has passed through, right? You never see that.
Well, in the case of Neptune, so the migration is triggered by the massive outer disk in the solar system, and once it was depleted by most of its mass, the migration of Neptune stopped. But you still have this cold population of classical objects, right?
Right, but they're outside.
They are outside the orbit of Neptune. And in that case, the planet is migrating inward. Yeah.
The planet at the end also gets some interest right now. It also gets eccentricity.
Yeah, because I think the particles are growing and getting mass, and you have scattering and gravitational interaction between massive particles on the planet. So it gets a little bit excited, yeah.
Part of this drift by eccentricity is also the mass that stays actually in the outside
Yes.
orbits of the planet. That's very important, right?
Uh-huh. Yeah.
Because that's the initial start of the Uranus-Neptune flip in the beginning. I mean, this is a very, very simplistic version of what is actually going on
Yeah.
in the solar system.
So Uranus-Neptune flipping is is controversial. We don't know if that happened.
Yes.
It occurs in some version of the NIST model.
Some version.
Yes. But it's possible, yeah, that Neptune and Uranus exchange their location in the solar system. But, okay.
My point is that the torques have to be considered all across the entire system. Right? So
Yeah.
there's mass, residual mass in the outskirts that pulls massive objects.
Mhm.
Via eccentricity.
Yep.
That's not what we do.
Oh, let's stop. All right. So if we want to understand the details of this planetary migration, we have to, if we want to understand how we got from this very flat disk of planetesimals to the present day architecture of the solar system. Well, it's a constant conversation, constant dialogue between three fields of research. So meteorite studies, because as I showed in the first lecture, from the chemical and isotopical composition of meteorites, we can more or less tell where they form in the solar system. Then we need to know the present day distribution. So that's telescopic studies of small bodies. So that's basically what I'm doing here at ESO. And then we did the dynamicist to make the link between the two, right? So I'll talk about what I'm doing. So how do we know which asteroids, what we see in the sky, correspond to what type of meteorites that we see in the lab? So traditionally, we've been using photometry or reflectance spectroscopy. So here is an astronomer at the VLT looking at an asteroid, and what he will see is a spectrum of a G2 dwarf. Doesn't mean that the asteroid is burning hydrogen, and it just means that it's a mirror reflecting the sun. And so we look at the asteroid, we take our spectrum, and then we point the telescope at the solar type star. We take another spectrum, and then you divide one by the other, and what you're left with is what we call a reflectance spectrum. So in that case, it's a S-type or V-type spectrum. So you see this very broad absorption band. We don't really need resolution in our field. So these very broad band are typical of silicates, in that case, pyroxene. And they are so broad because what you're seeing here is the transition of electrons in different levels of iron atoms. And this transition level are split because of the electrostatic field of surrounding atoms in your silicate crystallographic network, right? And so olivine and pyroxene will have two different reflectance spectra because this crystallographic order is very, very different, right? So we've been acquiring optical and near-infrared spectroscopy for hundreds of thousands of small bodies today, and people came up with these clever classification systems that we call the asteroid taxonomy, which are based on the reflectance shape, the shape of the reflectance spectra of the objects. So if I have to simplify, you have the S-type asteroid, which are silicate rich. So again, these broad features. Then you have the C-complex, which are carbon rich, more primitive surfaces. Some of them are hydrated, some other are not. Then you have these reddish classes, and then the N members, which are less common.
They're really called reddish. What's the name?
No, that's
Or the
no, that's how I call it. Because they have steep spectral.
No, I
so-
understand the reasoning, but I mean,
Yeah.
okay, it's one of the interesting.
Yes.
What's the difference between a T and an X complex? I read it wrong.
Oh, that's really funny you're asking because that's a question I asked. I emailed Francesca De Meo when I started my PhD and I asked, why did you create this class? It's basically intermediate, T is the intermediate in spectral slope between D and X. Yeah, but they're very rare. All right. So once we have this classification system, we want to know what each class corresponds to what object. And so the first success story was for well, three types of meteorite called powerdite, cuprite, diatonite, which are basaltic meteorites, and they were linked to the Vesta asteroid, which is the second largest asteroid in the main belt after Sirius. And they found this excellent spectral match between the reflectance spectra of meteorites studied in laboratory and the spectrum of Vesta measured at the telescope. And in addition to that, Vesta was imaged by HST, and they had multiple epoch images, so they did the shape reconstruction, and they found this very large impact basin excavation with a central peak, which is typical of impacts on the asteroid. And in addition, you have this huge family of V-type, so it's V because of Vesta, V-type asteroid collision family of fragments in the inner belt, and the inner belt is very efficient in providing material to the near space. So you have spectroscopic match. Vesta had a large impact. We see fragments everywhere. So now there's not doubt that Vesta is and its family are a source of meteorites found on Earth, right? And while we're here, I couldn't resist to show you this image of Vesta that we took a few years ago with Sphere. So you can see it's a decoupled image. You can see the improvement compared to HST. And this is an image from space, from the Dawn mission, and you can see the excellent spectral match, excellent match of geological features. So this central peak, and actually we can retrieve most geological features down to 20 or 30 kilometer size on the surface of Vesta. So we're actually doing geology and geophysics now thanks to Sphere. It's pretty nice. I don't know how much time I have. All right. Okay, so that was the first successful composition link between meteorites and asteroids, but now we worked a lot, and we think we have good analogs for each asteroid we see in the sky. We have good analogs in our collection of meteorites or our collection of interplanetary dust. So now we have a pretty good understanding of the compositional distribution of objects in the asteroid belt. For outer solar system objects, it's a little bit more complicated. But so what have we learned from that? So this compositional distribution allows to put very strong constraints on planetary simulations to understand the details of how Jupiter migrated in during the first million years of solar system evolution, how Saturn migrated, how Neptune migrated, etc. And I don't have the time to go through all of these models, but I'd like to talk about the concept that was learned from studying meteorite and asteroids, and that I think is relevant to people here studying exoplanets and protoplanetary disks. And that concept is fossilized ice line. So if we go back to this plot showing distribution of spectral types as a function of distance from the sun, you have this compositional gradient where you find preferentially dry asteroids in the inner edge of the belt. Then you see asteroids with low fraction of water, so from 0.1 to 1%. So when I talk about water here, it's mostly hydrated silicates, phyllosilicates. Okay, and then we have water-rich objects, which were probably implanted during the phase of planetary migration. They have a few percent to maybe 10 or 15% water in mass, in total mass. So that would put the ice line, the water ice line, somewhere around 2.1 or 2.2 astronomical unit when the solar nebula dissipated. But the question that was not well understood for a long time is what is the object beyond this? Why would the object beyond the snow line be so dry? Especially if you consider that in the solar system, water accounts for about 50% of the mass of condensable species, and I think that's also true for other planetary systems. So why do we have this lack of water? And answering this question is also answering the question, why is the Earth so dry? Because it accreted from similar building blocks. And it might sound like a funny question because 70% of the surface of the Earth is water, and in terms of total mass, it's quite low. It's 0.1%, right? And it's if you compare the inner solar system to other system hosting terrestrial planets, I don't know how reliable this is, but because this is not my field, but apparently in the case of the TRAPPIST system, the planet C, D, E, and F, which are in the habitable zone, they have up to 50% water. And a bit of water is good for life to emerge, but too much water is not great. So
Do they know that?
Sorry?
Is that solid? Any quantitative people? I think it's strange spectroscopy.
But that has nothing to do with the surface. That would be the atmosphere.
Yes. So, but yeah.
Density,
The
density probably.
Yeah,
I think it's density.
Yeah.
Yeah. So again, why is the inner solar system so dry? And so the solution, possible solution came from this very clever astronomer Alejandro Morbidelli, an Italian astronomer working at this observatory, and he came up with this concept of fossilized ice line. So in the protoplanetary disk, you had pebbles, particles that are created. So the protoplanetary disk was very warm. So the snow line, which is the limit at which a species can condense, in that case water, was quite far away from the sun, and objects that are created within the snow line, they would be completely dry, and objects that form beyond would be icy, right? And all of this will migrate inward. As the solar nebula cools down, the location of the snow line gets closer and closer to the sun, and so then these objects here were initially dry can accrete icy particles. But this happens until Jupiter reaches a critical mass, which is somewhere between 20 or 50 Earth masses, and then the planet carves this gap in the protoplanetary disk, or more specifically, it creates this pressure bump outwards of its orbit that effectively stop the migration of pebbles towards the inner solar system. And so the present day composition of the inner solar system would reflect the location of the snow line, not where it was when the gas was dissipated, but when Jupiter reached this critical mass that allowed to carve the gap in the protoplanetary disk. And so this makes a very interesting prediction, which is that a planetary system that hosts terrestrial planets without the giant planets beyond the orbit of these planets should contain much more water than that planetary system that will have a giant planet. So ice sheets that is created at the bottom of the ocean, and that isolates basically the rocky core, or the rocky core of the moon with ocean. So that's not very good for prebiotic reactions, right? So thanks, Jupiter. This is an example of how solar system science can teach us about exoplanetary science and protoplanetary disk. It was taken from this paper by Kane et al. I forgot to put the name of the journal, but I can give it to you if you're interested. And there's a lot of example of fundamental connection between solar system science and exoplanetary science, right? So let's see. I still have some 10 minutes, let's say. So now I come to space mission, which is the fun part of the presentation. So we had a lot of space mission to small bodies this past year. We had New Horizon to the Kuiper Belt. We had Dawn to Ceres and Vesta. We had Rosetta to Churyumov-Gerasimenko. I'll talk about the most recent one. We had return sample mission from primitive asteroids, basically twice the same mission, once from OSIRIS-REx from NASA and Hayabusa 2 from the Japanese Space Agency. They went to two different objects. We didn't know a lot about them before they reached them. We just know they were probably quite primitive, and when we had the images, they're basically siblings, right? And they have this very funny shape due to their fast rotation. And well, the samples from the Hayabusa 2 mission, the Japanese mission, are already on Earth. They were studied in laboratory. OSIRIS-REx is still on its way back. And well, we PAH amino acids, so potential building blocks for life. Yeah.
At least we didn't contaminate the sample.
I think they were very careful in that one. Hopefully not. Yeah.
Are they scared? It's like gonna blow up in their face.
That?
Yeah.
Yeah. Yeah, I don't know.
They might have some pyrotechnics in them.
Yes, it's funny uniform. Yeah, I don't know.
So regarding the contamination, they looked at the amino acids. So on the Earth, it's all left-handed, and if it's naturally, it should be both left-handed or right-handed.
Oh.
We have a little minimum access in the left-handed. And it says even there's a contamination, but it's minimal.
Yeah, very good point. Yeah. The chirality, right? Yeah. What else? Yeah, so the dust is actually quite similar to CI chondrites found on Earth, with the exception that here it was preserved from Earth's weathering. So yeah, very exciting mission. There's another, we had a another very exciting mission, which was, as you know, the DART mission, the first planetary defense mission that tested a kinetic impactor on a small asteroid. Actually, the moon dimorphos, so it's a small moon around a larger asteroid. You know, just in case if one day we find one of these objects heading its way to the Earth, we know how to deal with that. But what you may not know is that ESA is preparing a follow-up mission going back to Dimorphos, studying the orbital dynamics of the binary, and do a complete geological mapping of the moon, and especially the impact zone. We will see fresh material, so material that was not exposed to space weathering for a long time. Then okay, my favorite one, Lucy. So first mission to the Jupiter Trojan. So we've been to the Kuiper belt, we've been to the asteroid belt, we've visited several NEOs. This goes to the Jupiter Trojan for the first time, and in terms of orbital dynamics, it's genius. So the probe was launched in 2021. It will swing around the sun to get some velocity, and it will be sent to the leading cloud of Jupiter, the L4 Lagrange point. It will do 4 encounters of I think 5 objects, because one of them is a binary. Go back around the sun, get another swing, and it will be sent back. It will be sent to the trailing cloud of Trojans to see the binary system Patroclus Miniatus. I'm not sure how to pronounce that, and that will happen in 2033. It's a very long mission. The reason for the name of the mission, Lucy, is because Jupiter Trojans, they are believed to be they're relics of the very pristine objects compositionally from the outer solar system. And so they are like foci, of the solar system. So they were named after the Australopithecus Lucy, which is one of the oldest fossil of humankind. And Lucy itself was named because the how do you call them? The archaeologist, it's not archaeologist, paleontologist who discovered, thank you. So I think they were listening to Lucy in the Sky with Diamonds by the Beatles when they discovered the fossil, right? And this explains the diamond shape of the emblem of the mission. The first asteroid that will be encountered by the Lucy spacecraft will be actually a main belt object, which happens to be on the way, and it's called Donald Johanson. Donald Johanson is the person who discovered the Lucy fossil. Apparently, he was very happy to have an asteroid with his name. Yeah, next mission is Psyche. It's a mission that was supposed to go to a planetary core, because 16 Psyche was supposed to be a metallic asteroid based on its high radar reflectivity and because of its high density. But our team with Sphere, we made some measurements of the shape, so we computed the volume. We also have mass estimates, and each time we do a measurement, the density gets closer and closer to rock. So it's a bit sad for NASA, but I think it's okay because it's a very unique object. The radar albedo is really high, so it's going to be something unique anyway. And one of the specificity of this mission is that the probe is carrying a magnetometer, with the idea that if Psyche is the remnant of a protoplanetary core, we should be able to measure the remnant magnetic field from the core dynamo. Okay. And finally, Apophis. We don't have a mission yet to Apophis. Maybe we will, maybe we won't. But Apophis is really nature trolling us. It will be a 350-meter asteroid, so big like as big as the Eiffel Tower, that will pass within 6 Earth radii, so within the orbit of geostationary satellites, on a Friday, 13th. So heads up for crazy tabloid headlines about the end of the world, but definitely it won't impact with the Earth. But it will be deflected, and that's what extremely important about this object, because it can come so close to the Earth that we expect it to undergo earthquakes or asteroid quakes. So my previous supervisor from my previous postdoc, he wanted to convince the American Congress to give money to send a mission to Apophis and put a seismograph at its surface and measure these earthquakes and get information about the internal structure of Apophis. But unfortunately, we don't have a mission yet. That the flyby happens in 2029, so it's quite, even for NASA, it's a very short time to develop a mission and send something.
I have a question.
Yes. Everyone agree about this. It's model dependent, but it's possible that, yeah, it will
What
happen.
about the Earth? Are we going to be affected?
Only in Chile.
No,
You want more?
no, we're fine. We're fine. Yeah.
Nothing.
Just to give you a bit of goosebumps,
15 meters. Big oil tanks.
just to give you a bit of goosebumps, though, this is an actual simulation of what is going to happen seen from the asteroid. The time is accelerated 1,000 times. Sorry, those blue dots are geostationary satellites. So the asteroid will be first visible from Australia, and then
It's really close.
wait for it. So then it will pass above Africa. The closest point will be somewhere in the Atlantic Ocean. No, for
New York.
Washington, March. And then it will be visible from North America. There is a non-zero risk for satellites. It's most likely not going to collide because space is so big.
Why
And
don't we just use a satellite? A default one.
I know we just like put it into like somehow it's like it going through Starlink.
they're a bit too close to the surface of the Earth, unfortunately. Yeah. So it's a very rare event. It's an asteroid that big coming that close to the Earth. That happens every 1,000 years statistically. So it's not the century event; it's a millennial.
And every couple of years in Hollywood.
Yes.
Sorry, is it too fast for imaging with the GWST or HST?
I thought using sphere, but definitely it's going to be
Fast.
too fast. At least during the close approach, we can see it from far away. But
Yeah.
for James Webb, yeah, it will saturate. Yeah. Yes.
What is the minimum size of an asteroid that would kill us?
Kill us as the entire civilization, or as you personally?
Like just like have like a dinosaur event, you know?
Yeah.
Like obviously it's not gonna kill
So
like not like gonna kill every single one of us,
Yeah.
but like make it kind of unlivable and like
yeah, like regional damage, that would be around 100 meters, I think. But it's dependent on the orbit, how it impacts the atmosphere, the composition, and all of this.
when will that happen?
How long
So-
do I have left?
All kilometer-sized objects and nearest objects are known. There is no risk for the next 200 years.
You just said 100 meters.
Yeah, 100 meters we don't know yet. So there's a big effort. So they will have LSST that will discover all of these objects. Euclid will discover and then we have NEO Surveyor, which will be a space-based observatory dedicated to discover asteroid, potentially hazardous asteroid down to 140 meters. We will know all of them, and but smaller than that, it's not impossible that something happens. Yeah.
So how many does that asteroid hit Russia back in 2012 something?
Chelyabinsk, I don't know.
30-40 meters.
It's a few tens of meters and exploded and all the glass is shattered.
Yeah.
It depends where it hits. Right? It depends its composition, also what it does at the site when it hits.
It also came down with
Yeah.
waste.
Exactly. When its inclination is in first.
And
Yeah.
there's the woman got hit by a meteorite and it right off her valley and it's kind of went through the hospital.
I saw that on TV.
Yeah, but the shockwave in the atmosphere is what's dangerous. So in Chelyabinsk, you saw all the glass being shattered by.
That's how it's going to kill me by like glass.
Right?
So that's how it's going to kill me, like the glass shot, and it's just going to be.
Well, if you see a very strong light in the sky, you get away from windows.
You run away.
So I don't. As far as I know, at least last year they didn't have any mission approved to go to Apophis, but there's a possibility. Remember Osiris-Rex, so it's going to bring the sample from asteroid Bennu back to the Earth, and then they calculated with clever orbital dynamics that it can be redirected to Apophis, but only after the Earth encounter. So you won't witness the close encounter, but maybe we can see what the freshly shaped surface, asteroid surface look like. That I think is likely to happen. Yep. So that's the end. As always, I end up with self-promotion. I have a YouTube channel with some interviews of people working in the field. Some are directly linked to this presentation. So if you want to know more, I have this presentation about meteorites, capable attention to asteroids. And yeah, that's it. Thanks.
I don't know if anyone has more questions. We kind of asked them on the slide. So, yeah.
Quick question. So could you speak a little bit? You mentioned Kuiper belt and Oort cloud raised over the rest, which is actually really interesting in terms of information on our solar environment. Objects like satellites, like what do we do with this?
Yeah, extreme pianos. Yeah. I think Sedna is a recent scattering from Neptune, from what I know, but I'm not entirely sure. Whereas the Oort cloud will have mostly formed during when the massive disk of the solar system was depleted during the early planetary migration. Whereas I think Sedna is something, yeah, more recent. But yeah, I don't know.
This is what I'm asking you.
Yeah, I don't know a lot about the Oort cloud and extreme pianos. Sorry.
And maybe a follow-up question to this. So the most you were speaking about this fossilized
Ice line.
Ice lines, right? Of course, we are interested in investigating the objects in the more pristine conditions, right? When these ice lines have formed. Would centaurs not be the ideal tool to actually get into this, since they've been liberated out of the disk, right? They're high inclination.
The best tool to do what, to go there?
No, to based on their surface composition and their dynamics,
Yeah.
diagnose the early composition of the planetary disk.
Yes, like capable objects. But the problem is that we find evidence for cometary activity pretty far away in the solar system, and even in the case of Centaurs, it's possible that the surface composition has been processed due to volatile sublimation, CO sublimation, for instance. So yeah, they are definitely very pristine, but maybe it would be even better to look at the Kuiper belt.
So you would rather go out based on the radiation processing argument.
Yeah, so the cold belt would be the ideal place to look at very primitive material, but they are very small, very faint. Like they have a 4% reflectivity or albedo. So it's extremely challenging. But LSST will discover a lot of this object. LSST is going to provide a factor 10 or 100 for every number of objects for every population in the solar system. And then we have bigger and bigger telescope to do follow-up observations. So
how deeply can you follow this up? People just James Webb.
Yeah.
How thin can you, or how, let's say, small can you go?
Well, my target is oh, well, there's a big comet with like 18 AU. Yeah, so my target is like 10
Really out there.
No, it still has a limitation.
Yeah.
So James Webb can get near-infrared and mid-infrared spectroscopy for some dynamically excited TNOs that get close enough to the sun. For the cold belt, so they have low eccentricity, so they never get very close. And we are really reaching the limit of the telescope to get any good near-infrared and mid-infrared spectroscopy, but we got time to try, so we'll see.
It's going to be interesting.
Yes.
Meteorites from Mars.
Yes.
How can this happen? It's because they are, because of a high impact, right? That really spoiled the material.
Yes.
Not because of we are observing some of the pristine material in the formation.
No, no.
The formation of
They actually come from Mars, and first proof for that were the study of captured xenon and rare, how do you call it, these gases in the left of the periodic
Noble
table.
gases.
Thank you. Noble gases, which match the composition of the Martian atmosphere. But now we have rovers at the surface of Mars, and basically they are exactly the same composition. But all the Earth sample, they've been altered. So I told this story during the first lecture, but I have a friend studying the remnant magnetic field of Martian rocks, trying to know if Mars had a global dynamo at some point, which would have sustained an atmosphere and maybe liquid ocean and all this. And all meteorites were demagnetized by hand magnets, because when people look for meteorites, they use magnets. But we have the Perseverance rover, which is taking sample at the surface of Mars, and the follow-up mission, which is a collaboration between NASA and ESA, is sending back these samples to the Earth and study them in laboratory.
Yeah, sorry.
Well, what's your opinion on Planet 9?
No, I'm not a believer until I see it. So I'm part of a collaboration called the Outer Solar System Origin Survey, which discovered about the 800 TNOs. And it was the perfect sample because the discovery and characterization bias are completely characterized, and we can use a survey simulator to debias the population. And Planet 9, it was proposed to explain some alignment of extreme TNOs orbits, but without accounting for any discovery biases, because these TNOs were discovered randomly by different people and we don't know how. And also in our sample, there's not a single hint of orbit alignment. It doesn't mean it doesn't exist, it just means we don't have any proof.
You say if there's no evidence, then why would we believe there's another planet, right?
Yeah, exactly.
Based on that. So.
I understand also our planet has some Trojans. Are they expected to be similar to the ones around Jupiter or to belong to different boundaries?
Uh, the let's say it. Most people think that Jupiter Trojan were originated from the outer solar system, from the precursor of the Kuiper belt, and they were captured during the phase of planetary migrations. That's, for instance, what is described in the NICE model, which for a long time was the favorite model for explaining the architecture of the solar system. It has some problem because it has a phase of strong dynamical instability, so it destroys the Earth and the inner solar system, which is a bit problematic. But I think the dominant view is Jupiter Trojan. They came from the precursor of the Kuiper belt, and would be the same for instance, Neptune Trojans. And there's good proof for that. The dichotomy in colors, so even if they have different spectra, that could be explained by their closer to distance to the sun, but they have similar size distribution. They have similar bulk densities. So there's good evidence for Jupiter Trojan coming from the outer solar system, and Neptune Trojans would also be fed from the Kuiper belt.
What about Earth ones?
No, the Earth ones. So the Earth one are dynamically unstable, right? So they were. Do you know about this? Yeah.
We don't have stable Trojan
No.
population.
So they are.
The small ones.
It's like the mini moons. Sometimes the Earth has more than one moon. They are temporarily captured, and then they leave. So it's the same project for. So they probably come from the Earth's objects or the asteroid belt. Yeah, it's very different from Jupiter Trojan.
That's it. I think we can stop here. Thanks a lot.
So do these,